So, a very good afternoon to all of you who have come for attending the Green Carbon webinar series and the presentation today. I'll predominantly be introducing the topic of biochar, which can be used for energy storage and energy conversion applications. And it's predominantly from the work that I did at my PhD in NTU Singapore. And my dissertation topic there was based on carbon-based nanomaterial hybrids for energy storage applications. And the main PhD objectives that I had under this topic were to develop graphene-based composites for supercapacitors and to develop alternate biomass-derived carbon composites with similar or better properties. So I would, throw some light on the synthesis, characterization, and electrochemical performance, and some areas of interest predominantly dealing with regarding biochar and some projects and future research plans. So to start with, why do we even need to have energy storage and energy conversion systems? I'm sure you're all aware of the climate change, the pollution, and energy crisis that we are all facing today. So it's quite important that we develop clean and sustainable energy storage and energy conversion systems. So what are energy storage systems? I'm sure you're all aware of lithium-ion batteries, which revolutionized the world. So if you look at this particular figure that I've given here, it basically gives you a chart of the specific energy and the specific power. To elaborate more on energy storage systems, so any energy storage system has a particular specific energy or the ability to store a huge amount of charge and a specific power, which basically tells you the speed or the rate at which you can deliver this charge. So to read this graph, you can actually see that the electrochemical capacitors, which are given in blue, they seem to have a high specific power, but a slightly lower specific energy compared to your other batteries. So that's what makes supercapacitors different from batteries, which means like your supercaps can deliver a huge burst of power if you want, but then they cannot like store a huge amount of charge all at once. So currently, if you look at a lot of energy systems that we use in our day-to-day life, people usually tend to use hybrid systems where they utilize both supercaps for their high burst of power and the high energy density of batteries, which lets you store or which basically gives you a high energy density. So that's what you need to understand about energy storage systems, because any energy storage system is always, compared with this particular matrix, its specific power and specific energy. So we always look to develop energy devices with high specific energy as well as high specific power. And it's quite important to develop energy storage systems because to tap all your non-conventional or conventional energy sources like solar, wind, geothermal, anything, you basically need to store the tapped energy. So it's quite important to also have like efficient energy storage systems. So just to give you a brief description of what supercapacitors and different types of supercapacitors are, there are basically two types, or basically two different types of materials of supercapacitors, depending on the mechanism of charge storage, because basically you need your charge to be stored in this particular system, and then you need to be able to use it later on. So in electrochemical double layer capacitor kind of a material, the charge storage is very physical. It's mostly an electrostatic way of charge storage because there are charges which develop at the electrolyte interface. Whereas in pseudo capacitors, a different kind of capacitors, your charge storage is via an indirect Faradic or fast redox reaction process, which happen at or near the surface. So since your EDLCs, they have a physical nature of charge storage mechanism, they're quite fast. So they have a high power density because they can like quickly deliver the charge. Whereas in pseudocaps, since there is a chemical nature which is behind your energy storage, because of the fast redox reactions, it's comparatively slightly slower than your EDLC, making them, slightly lower in their power density. But given the fact that the redox reactions can happen both at or near the surface, they tend to have like much more capacitance, or the charge storage capacity, compared to your EDLCs. So for these reasons, like some of the examples for EDLCs are all like mostly carbon-based materials, and your pseudocapacitors are anything which usually have redox centers. So most of the transition metal oxides or your conducting polymers, since all of them have like a lot of redox centers, they do tend to be more pseudocapacitive in nature. So now, as I've mentioned, the two different, types of supercapacitors and their characteristics, I think it would make sense to all of you why we need to have carbon-based composites. On one hand, carbon-based materials are extremely fast, which can improve the power density because they can be, quickly delivering the charge, but at the same time low on their energy density due to, the limited space that's available at the electrolyte surface. We need to also incorporate the energy density possibilities in a good energy storage system. And for the same reason, it's quite important to have carbon-based composites. So some of the characteristics which would make a good energy storage system out of carbon-based composite would be to have the right ratio of components. Try to have more carbon instead of your metallic counterparts, because that can reduce your cost. So being cost effective. And another very important thing about energy storage systems is their life cycle. So you can basically think of your laptop charger, or your smartphone batteries. So all of them, like, as time goes by, they tend to, they don't store as much of charge. They tend to get like slow. Your battery runs out quite fast. So that's one crucial thing about developing like good energy storage systems. You need to have batteries or supercaps which can last long cycles. So that's where like supercapacitors are much more superior compared to your batteries, because they tend to last much longer, because the redox reactions are like quite fast and quite reversible compared to the battery mechanism, where the chemical reactions might tend to be irreversible as time goes by, giving them shorter lives. So a normal supercapacitor can last up to more than 10,000 cycles, or even like much more, compared to batteries which tend to have, at least one dimension like lower of life cycles. So I started with graphene-based nanomaterial composites. I'm sure all of you might have heard of graphene, which is a material, a carbonaceous material with an extremely high electrical conductivity, large theoretical surface area, excellent mechanical flexibility, chemical stability, and an inherent charge storage capacity. So I started with making graphene-based composites. I made two different sets of composites. One was with a conducting polymer and manganese oxide, which is a transition metal oxide. And then I also used ZIF. So ZIF is basically a metal organic framework, which is zeolite imidazole frameworks, which are extremely crystalline metal organic frameworks, where basically you have ligands and a metal center. So giving them an extremely good structure and crystalline structure. So I used them to derive nickel cobalt mixed oxides. So as I was talking earlier, here graphene would be my EDLC material, which would give me a high fast charge delivery capacity, whereas the polyaniline and manganese oxide and nickel cobalt mixed oxide, they're all the pseudocapacitive materials, which could give you much higher charge storage capacity. So I developed these two, and so I was comparing, like I was optimizing the right amount of components. I was trying to figure out, what is better of these two, and I applied it in supercapacitors. And if you see the black line here, you can make out that it's quite superior compared to a lot of other materials which are in literature. And comparing these two composites, like the nickel cobalt system and the manganese polyaniline system, my graphene nickel cobalt system clearly stood out. So now making graphene is definitely not, it's not easy, and getting the high quality, right kind of graphene oxide solution is definitely a very labor intensive, chemical intensive process. So that's what got me into thinking, like, can we replace graphene, which is a carbonaceous material, with something more sustainable? And that's what got me to biochar. So I'm sure you all know what biochar is. It's nothing but like plants or plant-based materials not used for food or feed, which predominantly comes under lignocellulosic biomass. They're heated in the absence of oxygen in a pyrolytic process. You get biochar. So definitely they're much more sustainable, have higher stability. It kind of also sequesters your carbon, much greener synthetic routes. You hardly use any chemicals. And they're much cheaper compared to your conventional graphene or carbon nanotubes, which are usually used in these kind of applications. So also like this, choosing the right biomass feedstock, like you need to think about how environmental friendly the entire procurement is, your low cost, easy transport, lightweight, shelf life, should be able to easily collected at source. So that's how I started thinking about the coconut leaf sheath, which is what I used as the feedstock. So as I was talking about earlier, my graphene nickel cobalt system worked really well. So now I'm trying to replace my graphene and put biochar or improve biochar to have like the nickel cobalt materials on modified biochar and see how it performs in comparison with your superior graphene based composite. So the first step was to develop a biochar based support, like biochar, or like I even activated it because it's quite crucial to have a high surface area for energy storage. And then I also like had your nickel and cobalt metal nanoparticles. I also nitrogen doped it because even that adds to your energy storage capacity. So the step A is to develop a high quality biochar support, which would let me grow the nickel and cobalt nanoparticles. And I did it like the usual. So for the nitrogen doping, I had urea solutions, and then I annealed it and I activated it. And I had like different sets to just make sure, what would be the best and optimum biochar support. And I compared all their electrochemical performances and even compared it with like the conventional graphene and conventional activated carbon supports. And two of my samples like did pretty well. As you can see, they were giving a specific capacitance. So that's the index which tells you like what is the charge that the material can store per gram. So now that I got my optimized support, the next job was to grow materials or grow my active pseudocapacitive materials on it. So even for this, like I needed to know what is the right amount of material which can go, what is the carbon to nickel cobalt ratio, which would be ideal so that you don't really like push a lot of your metallic particles into it, which can increase your cost. So the idea was to have an optimized nanomaterial loaded pyrolyzed biochar. So this is how it looked like. So on the left, you can see an SEM, which gives you a coral shaped matrix. So your biochar is completely filled with your active material. And you can also see the TEM image on the other side, where the particles are extremely small, close to like 70 to 80 nanometers, are all embedded in the carbon matrix. So how did these perform? Like if you actually compare the biochar based composite and the graphene based composite, you can see that the graphene based composite gives you a high energy density at lower pass. So when you actually have to deliver your energy at slower rates, your graphene based composite, the one in red, tends to be much better. But as you try to increase the rate at which you try to deliver your energy, it's not able to like store a lot of charge. But as for your biochar based composite, which is the one in black, you can actually see it starts at a moderate energy density, but it's able to keep it like even at higher power densities. So as to why this was happening, we kind of ran a study where the graphene based composite, it was basically like at high power densities, this charge storage is predominantly a diffusion based process for the graphene based composite. So as you increase the power density at the rate at which you want your charging and discharging to happen, what happens is there isn't enough time to form an EDLC layer or enough of redox reactions. So this scan rate is a major constraint because this being a diffusion controlled process, when your scan rates are extremely high, it's very difficult for the diffusion to take place at such a short amount of time gap. So as a reason, like your graphene-based composite is likely like tending to, not perform well at higher power densities. We also tested this for energy conversion, so which was basically as oxygen evolution reaction catalysis, and they seem to have a pretty good water oxidation kinetics, which is evident from the Tafel slope on, the second figure which is given there. And not to get too technical, this was just to tell you that it was not just used for supercaps or for energy storage, it was also used for energy conversion. The same material was used for energy conversion. We didn't have to do any modification. The same material which was used for supercap was used exactly like that, and it seemed pretty good. So we even tested it for lithium batteries, and even that wasn't that bad. So the point being, the same composite which you might be preparing in your lab, I mean, it could be used for like a lot of other applications, because especially in electrochemistry, if you have an electroactive center, it's quite easy to manipulate it for quite a lot of applications like supercapacitors, your batteries, water electrolyzers, metal air batteries, a lot of environmental applications, your fuel cells, and even biological applications. So having said that, these are some of my publications. If you want to like go into more detail into this topic, you could probably read some of them. And yeah, that's it. Open to any questions. Thank you.